Well, good evening, everyone, and welcome to the Hendrik de Waard lecture. First of all, we would want to especially thank you on behalf of Studium Generale, FMF, and the Stichting Professor Hendrik de Waard. And first of all, Studium Generale is the one who actually organized this lecture. They do a lot, Studium Generale, they sharpens your mind and expand your horizon with an innovative and multidisciplinary activities in the field of science, culture, and society. And I think it's really cool. They do a lot of things like these lectures, but also talks and workshops and stuff like that. As you can notice, a bit nervous, but it happens. My name is Kara. I'm the treasurer of the foundation, the Hendrik de Waard Foundation. And today I'll be your host for the evening. Hendrik de Waard is a foundation that was created after Hendrik de Waard, an honorary member of the FMF, retired 39 years ago. And since then, we've sort of continued his legacy of sharing scientific knowledge with the public by hosting a lecture once a year, like this one, by someone in the head of their field. Unfortunately, due to Paula de Waard, the widow of Hendrik de Waard, passing a couple of weeks ago, we do want to dedicate this special lecture to her. And for that, I would like to give the microphone quickly to Anita de Waard, the daughter of Hendrik and Paula.
Thank you so much for coming from very far away places like Bokstel, or even further away. So welcome to Groningen. We hope you enjoy the French fries, which we call not friet, but patat, as our speaker has learned today. It's a great honor and a pleasure on behalf of the Familie de Waard, who now no longer have any of our parents. My mother passed away 2 weeks ago. She was 97. She passed away in her sleep, and she would have said, "Mooier kan je het niet hebben." So she would have said she had a wonderful, rich life. Part of her rich life was observing people who did interesting things. She loved sports, and she would always talk about the soccer players and their transfers between different soccer communities. She also loved science, not as a scientist, but as a thing that people do. And she loved going to these lectures and watching, first of all, a lecture. Often she said, "I didn't understand anything, but what a nice person the speaker was." So she would see it as both, of course, science it's a meeting of minds, but it's also a meeting of people. And she hugely appreciated the fact that for 39 years, subsequent generations of students have carried on the H. de Waard lecture tradition. Tonight I learned that every new FMF bestuur, so all the people who were in charge of the FMF, had to visit my mother as part of a ritual to become a member of the board. So they're all nodding. She didn't know that, but she kind of suspected it. She always said, yeah, I think I am their mascot. And I think that was very well put. She was part of this group, and she felt very, very warmly towards all the students participating in physics and mathematics in Groningen, and particular the people in the FMF, where she was like, well, these kids are so busy, and now they do this on top of that. And so on behalf of her, but also the whole de Waard family, I want to thank you very, very, very much for carrying on this legacy. I'm very sorry she won't be there to meet subsequent new FMF besturen. We may have to invent a different ritual. Some of us still live in Groningen. We're happy to think it through with you. In particular, I want to thank bestuur of the Stichting Hendrik de Waard. I want you in particular, when we have drinks afterwards, to look closely at their ties, which they designed and had made and embroidered. And my mother always said, I have to give something to het bestuur. So I'm giving it to you now, and then I will gladly step aside. But thank you so much on behalf of all of us, and also on behalf of my mother, for everything you've done for her. Thank you.
So thank you very much, Anita, for the very nice words on behalf of the FMF and Stichting Professor Hendrik de Waard. Unfortunately, I've never had the pleasure of meeting Paula, but hearing the stories and all the other old boards talk about her, it's so nice, and it's so nice to know that you guys support us so much. It moves me a lot. Anyways, why we've come here today, the lecture from Kjeld Beeks about the redefining time through nuclear physics. Kjeld is someone from the Brabant who has studied applied physics as his bachelor and his master's, and then did his PhD in Vienna on the nuclear clocks, but also has created something called radioactive crystals, which we'll be hearing about also later. And I think it's time to just pass on the microphone, because we have some very interesting talk coming up. So give a round of applause to Kjeld. But one more note, we will be taking pictures in this event. But for Kjeld, can I have a round of applause?
Yes. Can everyone hear me well? Just welcome to this very beautiful evening of the Hendrik de Waard lecture. I think I might have one of the most applicable talks in years, also about the research that Mr. Hendrik de Waard did, and so I hope to do justice to his honor. So I want to talk to you about time and about nuclear physics. These two things are not often talked about, especially nowadays. And I want to tell you that there's some sort of cycle happening between the two. And one important part is spectroscopy. I will explain what spectroscopy means, but people do a lot of spectroscopy in physics. I just heard it again, like spectroscopy. And through spectroscopy of nuclear physics, we've learned things in order to define time and measure time. And yeah, still, I would rather say that the way time affects nuclear physics is that we need about 40 years to get like anywhere again. So this, the time scales of science are in general very long. So let me just give you a little bit of introduction of like basic knowledge that you might need, such that the rest comes a little bit more fluid, let's say. And that is also what I want to keep saying in my lecture. Like, I want to always explain to you why we are doing this first, such that you can then maybe focus on like, oh, how are we actually doing it, right? So Nietzsche was kind of like, okay, you can bear through anything. So I hope you are a bit excited about science, but if you need to bear through it, then you just need to know the why, right? So why even attempt to research this, right? A very general question. Why do we research? Well, I mean, for the economics in there has been studies, so you can tell this to all your friends who are like, why should I be in science? That if you spend $1 on R&D, in general, 5 comes back to society. This might take very long, but in general, investing in research, and especially if somebody needs to vote on Wednesday, this is apparently something that really pays back in the long run, right? So that's why we do science and research time, nuclear physics. Then let me go back to one of the most famous physicists to explain some of the basic concepts. Of course, Albert Einstein, and he had two very clear points. The first one, a bit introduced by Max Planck, but energy is exchanged only in discrete amounts. That means in like a package. So here, just like what we like to believe a photon maybe is, like at least that's what AI thinks a photon is. And as physicists, we like abstraction. So how do we draw this photon? We're kind of like, okay, there is a system, and we describe the system with two levels, the two horizontal bars, and there's an excited state, the E, and there's a ground state, the G. So and then there's an arrow in between because the system changes over time between one state to the other, and then what happens is it emits a photon. But there's a certain energy change that is between these two states of whatever system I have, right? This can be turning on and off a lamp. This can be starting your car. This can be the sun exploding. I don't care, whatever, abstract. And this energy change, what Einstein figured out, can be described by this equation. So the change in energy is some constant, h, times the frequency of the photon or the wave, or divided by the wavelength of the photon. So how long the photon is, or how many times the photon goes up and down in a certain time, the frequency. Very important, keep this image, zoom in on it, just keep it in your mind. Well, now the second point is a way more complicated point and has to do with time. Effectively, what it means, there's something that one thing can only happen relative to the other thing. There are no absolutes in the world, I would say. Only absolutes that we made ourselves, everything else is relative. And this also means, for example, that the closer you are to Earth, the slower time actually moves. We know this. Time is not a constant in the universe. Like, it depends on how fast you're moving. So that means that if we define or we talk about time, it's like 12 past 8. If we talk about time, it needs to be defined towards a reference frame, and usually we say Earth because that's convenient for us. But if we would have somebody on Mars, that would be a more complicated issue, how we would define time actually. And in general, we don't know what time is made of. We don't understand it very well. But what this means is that what you need to remember is a clock can only show time with respect to another clock. So you always need to compare two clocks. That's why we have defined time. Maybe you remember this image of the meter stick in Paris, like this is a meter. Well, we also did the same with the second, this is a second, because everything is relative. We need to say this is a second. So those two things, right? This is a second, everything is relative. Quanta, energy comes in quanta. And then one of the most powerful techniques in physics that we have, spectroscopy. Well, we have our level system, the excited and the ground state, but usually a system has more states. So it has several states, like, 3 more, infinite, depends. And this is applicable to any fundamental system, can be a quark, can be a nucleus, an atom, a molecule, a car, any system. You can sort of abstract divide into these kind of levels. And what we then do in spectroscopy is we take the energy quanta that come out, like Einstein said, light, for example, and we use a prism, for example, to separate it into its different colors. And then we get something that we like to call a spectrum. And here you see a spectrum where you see horizontally the wavelength of light, and in the vertical direction is usually intensity or so, like do we see something? So you see there, we have some peak around 600, in this case, nanometers. There's no units, see? That means that it's about 2 electron volts of energy. This unit is maybe not familiar to everybody, but just remember this is 2. So light that comes from a sodium lamp outside is about 2 energy. So spectroscopy is very important, and also Mr. Hendrik de Waard did a type of spectroscopy called Nussbauer spectroscopy, named after a different physicist. Well, here's a picture I found of him, a lovely picture, well lit, I would say. And what is Nussbauer spectroscopy? I explain this because this is also, all these things will come back, all important. So you take a nucleus, which has an excited and a ground state, and then when that nucleus decays, usually due to some radioactivity, then it emits a photon. And this photon has energies of kilo electron volts, or thousands, maybe even millions of electron volts. And what he did was he took another nucleus, and of course that nucleus has the exact same, because all nuclei of a certain type are the same, has the exact same level structure, but that would be boring, right? So what he did, because then you could just excite it and you would know. So he put it into a material. And if you put it into material, what you get is you get more energy levels, you get substructure, you get something interesting depending on the material that you put around it. And so now what you can do even is you can shake this nucleus, and I mean literally shake. And what happens is the Doppler effect. Is there anyone who does not know the Doppler effect? Free to say. Yes, to the left. So the Doppler effect is when you have an ambulance that makes a sound, and if it comes closer, the sound becomes like a higher pitch, so the frequency goes up. And it means that a moving object will sort of in general compress the wave or expand depending if it's moving away or towards you. Right? You have to say, yeah. And so if you, it works not just for ambulances, but also for something as small as a nucleus. If you shake it, different colors of photons come out, depending on how fast you shake it. And then you can do actually spectroscopy on all these levels. And if you then measure that, you get an image like this that I took from one of his papers, where you see on the horizontal axis velocity, how fast do I shake, and on the vertical axis intensity, and then you see, I can see this wonderful structure, and then I can relate that to the material that I put my nucleus in. So you can learn something about the material you're studying. But there's one thing that is, I have to mention here, this is usually things in the environment become messy, right? Like if you put something on the street and it becomes messy. So it's actually very interesting that he sees these very narrow lines as really, because you would expect to not see any substructure. It's because, in general, nuclei, they don't interact much with the environment. So he described it as bevroren kernen, or frozen cores. This can also be called the Lambdike regime, or conservation of energy and momentum, for the physicists out there. But this is important. So a nucleus in a material tends to be frozen, and you can actually, it doesn't interact so much. It's not messy. It's very clean. That's an important point. So this was like just an initial physics. So any questions about this? Like sort of get the concept? Yes?
What's the excited state of a car?
I think broom. Right? Okay. Let's continue. So when people think of time and nuclear physics, very often what they think about is the doomsday clock. And every year there's still physicists in nuclear physics that bring out a time that we are before midnight, where midnight is absolute destruction of human civilization. Now we're 89 seconds to midnight since 2025. And if you look at this statement, it's actually very interesting because they actually say that the United States cannot be counted on to actually do nuclear physics for peace, but China actually can be. Just so you guys know, because China is actually apparently trying to, keep peace in terms of nuclear weapons, and the US less so. Like why is it important to keep looking at these things? Because nuclear weapons were forgotten for a very long time, and then with the war in Ukraine, they were again brought up to a certain degree. Well, it's because of this, right? And I can give you a moment to actually look at it. You don't need to look at me, because I find it something very powerful. You can literally, this is something, I don't know if everyone has ever seen a rocket launch. It's something that feels completely out of there, and it's because of its destructive power, right? And actually, when the time that the nuclear bombs were built and made, the Manhattan Project, they were at, like 2 minutes to midnight. So we're a bit worse off than they were in 1947, I think. This might tell you something about the times that we are in, right? This as a general introduction, because I will make sure that all of these things are important in talking about my research. So now, the history of a nuclear clock using thorium-229, which is a specific element and a specific isotope. So this Manhattan Project, was fancy and in the news and hype in the US, and at some point in 1946, somebody figured out, Mr. Glenn Seaborg, that there's a third fissile material, a third type of uranium that we can use to make bombs, uranium-233. So here is he, Mr. Seaborg, and effectively what they did was they took a really, really, really big nuclear reactor in Hanford, and they shot a lot of neutrons at thorium-232. Watch the number, different isotope. This one is stable, and you can find in nature. This process is also the thorium reactor, right? Like some political parties or something are talking about thorium reactors and stuff. That's doing this. You shoot neutrons at thorium-232, and out comes uranium-233, which is fissile, which can produce energy and can be used to make bombs, right? And what is interesting, so if you look at the so-called decay chain, because when something is radioactive, it tends to change from one element into the next one. So the uranium changes to thorium, changes to radium, changes to actinium, all the way down to lead, actually. And like I already kind of like foreshadowed, we like this thorium one. And the question is like, why do we like this thorium one so much? And just to put things in perspective, what they did, it's insane because, you know, people forget that producing material with nuclear reactions is very inefficient because they used 860 tons of thorium to produce 1,500 kilograms of this uranium, which they needed to research, can I make bombs out of it? And that has actually decayed to 350 grams of this thorium-229, and there's only 12 milligrams sort of available usually. And that's what I'm working with 12 milligrams of material on the world. Well, we don't count what Russia and China has, but they have some, let's say. I have stories. But okay, let's go back again to this powerful technique of physics, spectroscopy, because we physicists like to look at the structure of things. So they made this uranium, and then, of course, what did the physicists do? They looked at the spectrum, what photons are actually coming out. So they looked at what photons come out of this thorium, and then these people, Kroger and Reich in Germany, they found an extremely low-lying nuclear excited state of less than 100 electron volts. So I told you that the lights outside is 1. Most nuclear things are 1,000 or 1,000,000. This is less than 100. So you see here the energy levels, more complicated now. And there's like hundreds of kilo electron volts. So there's like 100,000, 1,000,000. And then they're all the way on the right. All the way on the right, you see, there's this little one just above at 100. But they only knew less than 100. And this was interesting to some people. So in general, people started researching this, but there was a little bit, again, because of society, there was a bit of a delay of like in the 70s and 80s where we were more preoccupied with other things. But then people started measuring these spectra again, and they started looking, and it was like, this is actually very interesting because this energy is so low, 3.5 electron volts, that one can actually probe it with light. It's just visible light. It's not X-rays, it's not radiation, it's something you could see with your eye. That would be unique, a nucleus which shoots something you can see with your eye. And so then, obviously, there was a theorist in Russia, Takalia, who actually proposed some applications. Like, what could I do with such a nucleus that I can manipulate with light? I can shoot light at it and light comes out, like that I can see. So then he was like, the existence of such a level in thorium-229 gives a unique possibility. So he says measuring the half-life in solids, so more for solid-state physics. One is developing a high-stability nuclear source of light for metrology, not to be confused with meteorology, which is weather, and making a gamma laser, right, a nuclear laser. And so we, at some point, focused on this middle point of his ideas, this light source for metrology, which people would call a precise clock. And the point now is, I guess, the question is, what is precise? Right? What does it mean? What physically does precision mean? Well, I found this really nice poster in a museum that Rolex probably wouldn't want me to show anymore, where they were like, if you shoot rhinos, wear a Rolex, because that's precision, right? You shoot the rhino. This happened at some point. Luckily, we progressed as human society. There was also some philosophers who were thinking about precision, where they were like, well, actually, the moment we started measuring time, we started to believe that there is sort of an order to the universe, because the clock keeps ticking. And he was thinking, did that have anything to do with the fact that also in science, we started believing that the world has order? Because honestly, there's no proof. I mean, it has a certain amount of order, but we don't know if it's perfectly ordered, right? But usually what we would, in physics, in practical terms, what is precision? Well, here I took a picture of the Martini Tower because I thought it beautifully illustrated my point. Can you see what time it is on the clock? What I think it's about like 9:45 or so, but you can't really see it, right? It's a bit of a bad picture. So that is exactly what precision is. So precision is, you look at the church clock and you're like, it's 9:45-ish. And then you can look at your phone and it says it's 21:47, 35 seconds, 100 milliseconds, whatever. So super precise. But I have to say that we don't only care about precision, we also care about accuracy. Because maybe you can also look at the Martini Tower and then you're like, I didn't change to winter time yet. So I'm maybe precise but not accurate because my clock is still an hour off, right? And that is the difference between precision and accuracy. Right? So you can be very precise and not accurate, and you can be very accurate and not precise, and ideally you are both. So now you know what precision is. The question is, what is a clock? Right? Well, a clock is something that moves regularly at a stable frequency, and a clock can be honestly anything. So usually, as physicists, we describe things abstract. So we take this little wave, moves up and down, and that can be the pendulum of a clock. That can be the sun coming up and down. And in general, what you would do is you would take a point, let's say the sun at its highest point, whatever, and then you would actually just count. If you know that, okay, there's about 1/4 of a second between 2 points, and then if I just count 4 points, then a second has passed, right? This is how a clock works, and you calibrate it or so, because, again, everything is relative, right? So the second is just something that we define ourselves. So you take what you think is a second, and then you count 4 times the pendulum. That's a second. Okay, cool. But I also talked to you about this energy level before, right? Where Einstein already showed, okay, that is a frequency. And, well, a frequency is nothing more than, 4 ticks per second. So actually anything that has a ground and an excited state, maybe even the excited state of a car, could be used as a clock. If your neighbor always turns on the car at 9 a.m. in the morning, then you know that's 9 a.m. in the morning. And so actually it means that anything that can emit and absorb a photon can become a clock. And that is how we nowadays build clocks. One more important point is we usually care about the quality of our clock, and we describe that as the stability over the frequency. So kind of like, okay, how stable is this frequency that the pendulum is, right? Because the pendulum is stable, but it usually slows down over time due to friction, so it's not completely stable. And also, the frequency is important. Why is the frequency important? Well, it's about averaging, right? I have this piece of paper. If I want to measure the thickness of this piece of paper, I won't just try to measure this, I will just fold it, like as many times as I can, and then measure the thickness and divide it by how many times I folded it. It's a way more precise way to measure the thickness of a piece of paper than doing that. So that's why the frequency is also important. So the higher frequency of a clock, the better it is, and the more stable it is, the better it is. That's the basis of all clocks, I would say. And so how do we do that nowadays? All right, usually we take something like a laser, which is again a wave of light. And what we do is we take some atom that has an electron flying around. This is familiar to people, just not to a certain degree. There's an electron flying around, and this atom can absorb and emit the light. This is this 2-level system, right? So we can make a clock out of this. And the thing is, though, unlike nuclei, atoms are not so shielded from the environment. So usually we put it in vacuum, just nothing around it. It's easier. Actually, you're just doing spectroscopy again, right? This powerful technique that we have. And again, what you do is you just count how many oscillations of light I have, and then I say, okay, maybe 1 million of the oscillations of my wave of light is a second. And then you can ask me, that's like a very difficult question actually, how do you measure how many, because it's super fast light, how do you measure light going up and down? Well, that's something you do with a frequency comb. If people really want the details, ask me later. But a frequency comb is basically a pulsed laser which can really count, okay, that is, because it's very fast and very narrow and phase stabilized, etc. It can actually count the frequency of light. And this frequency comb is important because it will come back later in the talk. Somebody won a Nobel Prize for it because it's essential to modern spectroscopy. Well, now, what can we do, right? I wanted to always explain to you the why before the how. So what can we do with those atomic clocks? Like Einstein said, the passing of time can only be shown when you compare clocks. And luckily for us, every atom in the universe is the same, at least as far as we believe. That means that you can compare two atoms and you get super precise measurement, because like no two cars are the same, but two atoms are really very the same. So this is super powerful that you can compare these things. They are extremely sensitive probes for the environment, right? So what we do actually is we use these clocks for GPS. So effectively, GPS is nothing more than getting times shot at you, and then you say like, if I compare all these clocks, then I know where I am relative to the satellite that sent the signal. And you need to be super precise for that, because if you go actually to this website, if anyone is bored, you can check your phone. It's time.gov by the US. It lets you check how bad your clock is. And I checked on my smartphone, and my smartphone was off by minus 1.1 seconds. And that's pretty bad, because if you imagine that the speed of light is about 300,000 kilometers per second, that means that if I would use my phone to do this, like try to measure where I am, I would come out somewhere far off Earth. So that wouldn't work. So the precision of these GPS satellites to tell time has to be at least on the nanoseconds level. It has to be very, very precise. Otherwise, you would not be able to tell where you are. And so this is something that everybody uses, and people also use in tons of experiments. Like it's unimaginable how useful it is to have this. So that's why we make clocks. Then obviously, what I preceded before, you can ask yourself the question, what is time? Well, I think there's really something revolutionary happening in there now, but I will not talk about it. It's a great discussion point for after the talk. It's really very deep, and it's very hard, I would say. One last question, because it's Studium Generale was about culture, science, and politics. How much time is left, right? Like, again, the time. Well, some people believe that we have 3 years, 268 days, until we have 1.5 degrees of global warming and all goes to shit. Then I checked for a moment, like Groningen here, they vote for GroenLinks PvdA in general, like the polls. The polls for this year, they say that this is how the Chamber of Parliament would look like for Groningen in 2025. So let's see what happens on Wednesday. But so I just wanted to highlight, so what does it mean if you vote for these parties? And then specifically on nuclear physics, because that's what I'm doing. So, I mean, you can maybe, I didn't put which party, but it's the top 3. So the first one says, we don't want to build nuclear power plants. 0. Nothing. Doesn't make sense. The second one says, well, we want to do green, but we're open to nuclear energy. And the last one is make many more, all small and thorium reactors. So actually it would be very good for my research, because it means more of this process, which means I get more thorium-229 for my research. So honestly, I don't know what I vote yet, I guess. No, as a Dutch person living abroad, I already had to vote by mail. So how can these clocks help to solve these fundamental issues that we have in society? Is kind of let me subdivide them in fundamental physics, which is what we find interesting, and solve mankind's challenges. What we do to a certain degree is we can measure drifts and fundamental constants. And this means if we measure that, it means there's new physics somewhere, and that excites us, because we can, like, we know, like, oh, okay, there's like, I don't know, we can figure out what time is, we can figure out what gravity is, we can figure out what quantum physics is. And so that's something you could really measure very well with clocks. Also improving the understanding of nuclear physics. So for the up-to-date physicists in here, for example, you have the kink plot of ytterbium problem. We don't understand it, and it's because we don't know enough about nuclear physics. And we obviously can keep on testing Einstein. He is still right, sadly, after about 100 years. Well, solve mankind's challenges. So you have, you can navigate your troops of your army during a GPS outage if you have precise small clocks. You can do more precise missile strikes, for example. You can also do oceanography on maybe the more nicer side of life, and you can do atmospheric sciences very well using clocks. And the example that they usually give is this, is that if you have a ship that sends a sound pulse that can actually travel through the ocean floor, and you can actually measure reflections of this sound pulse on different layers. And so you can use very precise clocks to really precisely measure, okay, this is all that's in the bottom, and you can learn lots of things, and you can, protect the environment, etc. So there's, as physicists, I would say, again, politically speaking, there's choices that we can make on which of these topics we want to contribute. So why would this nuclear clock now be better than the other clocks, right? Because I talked about other clocks and nuclear clocks. First of all, clocks always need to be compared. So if you want to have a good nuclear clock, you need a good other clock, let's say. So we are complementary, collaboration, not competition. So here I have another figure with, on the horizontal axis, the half-life. So how fast this excited state goes to the ground state. And in the vertical axis, energy. And this is the logarithmic scale. So this is like, it goes from 10 to 100 to 1,000 to 10 to 100,000. And all the blue dots that you see are nuclear excited states. And the red dots are states, like excited states that we use to make clocks. So those are already clocks. And then you see that this thorium that we like, that has this really unique nuclear state, is exactly in the same region as all these other guys. So that's why we like to use this one. And, it means that we can transfer technology that's already there on how they do these optical clocks directly onto this nuclear clock. But this nuclear clock is obviously a very new and unique system. That's why we're interested in it. So, because the nucleus is really small. It is 11.5 femtometers, that is 15 zeros, versus a nanometer or an angstrom, like that's 10 zeros. So it's 100 times smaller than the electrons. That means it's less sensitive to the outside world, as I already said, what Hendrik de Waard also actually used. And also in the nucleus, for the physicists out there, there's more things happening. The electrons are only guided by the electromagnetic force, but the nucleus has strong and weak forces that play a role. And so what we always like to say about this unique thorium state, which we by now know is around 8 electron volts, which is kind of light that you can see, but you can't actually see. But you always have to remember that because the forces at play in the nucleus are so strong that this is such a tiny little difference. This, if we can build this clock, it would be an extremely sensitive probe to lots of new physics. Because imagine if one of these big blocks even changes by a little bit, that would have a huge effect on this excited little state of the nucleus. So if you have a 1% change of 50,000, that's still 10. And well, the thing that we're looking at is also around 10. So this tells us that it should be a very, very sensitive probe to the environment. Well, so I now talked a lot about why in terms of society and nuclear weapons and what we can do with these clocks. So let's go to the how, right? And warning, like we are going now into more physics territory. So if you didn't study any physics and you're like, I don't really get it, just follow the big lines, right? Don't try to follow every word I say. So how did we build this nuclear clock? Step 1, we built a container. And we were guided by the same principles as Mr. Hendrik de Waard. So what we decided is this vacuum, really not it for us. Let's try to put it in a crystal. So what I did in my PhD was I grew crystals. They kind of looked like this. And we have 0.1%, so 1 in 1,000 of our thorium that replaces a calcium. I'll get to that in a moment. And we made them even smaller. So this is like this big. That's how big we in the end made our crystals. And so what is happening here? So we have a crystal, an ionic crystal like salt. It's very similar to salt actually. That is made up of calcium and fluoride. You see them there. And then we sprinkle a little bit of thorium in there. And it actually likes to sit in between all the calciums and take up the position of the calcium. But as you can see already in this image, because thorium has a 4+ charge state, it doesn't have the same charge as calcium, because calcium is 2+ charge state, we need to have 2 extra fluoride negative charges to sort of compensate, because in the end, things tend to be neutral, right? They don't tend to be supercharged. Yeah, so we prefer the crystal over the vacuum. So yeah, my name is Kjeld Beeks, and actually I baked crystals. Only works in English, that joke. But of course, this was not just me, this was everybody in our team. And this is me in the lab with actually a uranium-doped crystal. And yeah, growing crystals with radioactive material is hard because you have to do a lot of safety. but it's actually manageable. You should just not lick the crystal. That's kind of became the staple, like, okay, you can handle it, you can work around with it, but I mean, just try to not eat it, right? And it's manageable. So I like to see this usually as baking cake, not this cake, like actual cake. So let me go through you how we made these crystals, because it's actually important. So talk about the dough, like the calcium fluoride and the thorium in there, a little bit of baking, like for, I don't know, for the people who like cooking, spicing it, like, I don't know, we have all kinds of questions. Why? Because we first made very bland cake, like it didn't taste like much. I'm also a bad baker. I don't like to bake, actually, in general. And in the end, we did spectroscopy, a little taste test of our little crystal cakes. So the physics, right? Here it comes. So we have our thorium. And like I said, we like to put it, our thorium is radioactive. It has an 8,000 years half-life. That means it's relatively stable. It doesn't just disappear before our eyes. And it has this narrow nuclear excited state, right? This nucleus is frozen in the environment, as we've learned before. So we can put it in a crystal. And we have a really big benefit because the other clock, right? That's like, they usually have one ion sitting in the vacuum, but we can have like, what, I don't even know, it's that number, it's like 15 zeros, right? So we can have many of these nuclei in a crystal, and then in the end it looks like this. And we put it in calcium fluoride. And why did we choose calcium fluoride? It's because calcium fluoride has a simple structure, cubic, easy, just a cube, no rectangles or parallelepipedums or whatever. It takes dopants, we know that, so we can put something in there that doesn't supposed to be there, intensely studied, and very important, it's transparent up to a very short wavelength, such that we can actually do spectroscopy on it, right? We need to send light in and light needs to come out, right? So in and out, very important. And we need this compensation of 2 extra fluorides when we put it into calcium fluoride. So the first thing we did was theory, because theory is very important, guys, not just experiments. We tried to calculate, if we put the thorium in there, how does it change the color of the crystal, right? Is it still transparent for the wavelength of light we want to use to excite this nucleus? And then you need to actually be very creative. You need to start thinking, okay, how can that fit in there, and where can we put the fluoride? So you get all these different geometries, we call them. And, but it's not too important. In the end, we do the calculations and we can kind of sort of figure out that, okay, it's still transparent. It gets a little bit less transparent because of so-called defect states. So there's extra things you can excite, right? Like what I said at the start with Hendrik de Waard, in general, if you put something in something else, it will change. Like it will interact with its environment. So, and I just want to say a little bit more on the dough that we use, on the calcium fluoride, because this will be important also in a moment. The fluorides, these F things, another element that are sitting on the corner, they are very mobile. They tend to move around. They tend to create defects, like what we call a fluoride vacancy, or a double fluoride vacancy, which actually produces a very pretty orange color, like there on top of the right. Like I could just show that with a laser pointer in the lab. And they also have something that's called the self-trap exciton, not really very important. So they have this calcium fluoride, it's cubic, it has defects, complicated, rich physics. But let's get it down to earth. How did we bake the cake? Well, what we just did is we took a very small crystal. It sounds super stupid, actually. Like you think high science, but it sounds stupid. We took this crystal, we put a little powder in there that's on the left, really just sprinkled some powder in there. Then we melted it, and we did it with a very steep temperature gradient, such that only the top melted and not the bottom, such that we could grow one crystal on top of the other. Like maybe you've done that in chemistry, you grow crystals on top of each other. And then in the end, we cool it down and we have a beautiful crystal doped with thorium, which is what we need, because we need to have our thorium somewhere that we can do the spectroscopy on. And usually that looked like this, right? You see that the thorium, in this case, the uranium in this case, colored the crystal. It made the crystal more red. And this is because of this interaction between things, and you create different excited states and ground states. Well, for this, you need actually a very good oven. This is how it looked like. It's a vacuum system. There's a really tiny crystal in the middle, lots of graphite that is by now laced with radioactive material, and I have to clean up by now. And this was a lot of engineering. So physics is not only being in like theory and things, lots of engineering. We needed to use 1500 degrees Celsius. We needed like fluoride resistant materials, et cetera, et cetera. But okay, we did all this stuff, and then we had a problem in the end. Because all the crystals we grew before came out beautiful, but then we put something radioactive in there, so growing these radioactive crystals. And what happened? The crystal was opaque. It became like this, like milky. And of course, you cannot do really spectroscopy on a milky thing. So actually, many people like kind of gave up. They were like, okay, this is never going to work. Then we did a lot of thinking. And we actually figured out, like, when we put this radioactive thing in there, wow, it's molten. What you see is that due to the radioactivity, the fluoride evaporates. And we end up with a crystal that has too little fluoride. Like your teeth, right? You brush your teeth every day with fluoride, because that gets lost and you can add it again. So then we developed a technique where we actually put the fluorides back. And this fluoride vacancy that calcium likes to make, you can fix that. And so you can really see that the crystal, there's like a little cloud in the middle, so you can see like the milkiness reducing, and it's just by removing fluoride vacancies. So making the crystal more perfect again, and we developed some fancy technique for that. And this was really the key. So if like now we get lots of results and these clocks are working, the key was understanding what was wrong, engineering a solution, and then things started going. Because then what we did was we, wait, just a moment, sorry. So we obviously kind of still, to get to this point, so how we got to this, a little explanation, is we used again theory. So again, this balance between experimental physics and theoretical physics, where you really learn from one another, is extremely important. So collaboration, guys. Because what we did was we did simulations of the spectrum of this milky crystal, which was not good for us. And then we could actually figure out which configuration this thorium had inside the calcium fluoride structure. So we could like make these little structures happen here, and we could see like, really with this technique we developed, we can remove the fluorides and make the crystal transparent, because this reduction is obviously the crystal becoming transparent. And this we only could figure out by doing a lot of theory and a lot of experiments. And well, in general, this means that I produced a lot of crystals to try and understand all this behavior. So I produced a ton of them. And at the moment, there's actually only 3 of them that are good. So it's more like legacy material almost. So we have 3 of these thorium crystals, and they're really tiny, right? See, 1 millimeter, 3, 2 millimeters. And they have a certain concentration, and they were grown actually almost 5 years ago. But they are still producing a lot of results, because from this point on, these crystals were working. And what we then did was, obviously, as any good scientist should do, we collaborated. So we took these crystals from Vienna and we sent them to Japan, where they actually managed to excite the nucleus with X-rays. We sent them to Germany, not so far away, where they did the first laser excitation of this nucleus. And we sent them to the US, where they did the first actual production of a thorium nuclear clock. Now, to zoom in on this, this sounds easy, but this was not completely an easy journey, because we needed to find where the frequency or energy, right? Think back of Einstein, where the frequency of energy or energy was of this thorium nucleus, because we only knew it very roughly, because this graph shows kind of what we knew, because here on the horizontal axis you just see time, years, and in the vertical you see kind of like what we thought the energy or frequency was. So first it was less than 100, I talked about that. And then we were like around this 3, and then we slowly went up. But the last jump, when we first managed to actually do something with our crystals, is so tiny that you can't even see it. It's 800 times more precise than all the measurements done before. And that was because the crystals worked, and we had lots of development in laser physics, lots of development in laser technology, which I won't be talking about. So what we did was a process called 4-wave mixing. This is relatively well used by now, but it's more for the physicist, because we needed that to produce the color of light that excited the nucleus, which was sitting inside of the energy levels of the crystal, right? And how does a physics experiment looks like? It looks about like this. So there's all kinds of electronics and optics in the vacuum. And what we managed to do here was we managed to find this energy, and it took us years, right? So we spent years just changing the energy of our laser, scanning, trying to finding nothing. So physics is 99% failure, guys. Like, that's what, I'm presenting the success, but it's 99% failure, maybe more. And then you see that, well, on the top you see a peak, and in the bottom you don't see a peak, and it's actually very important, because we used a different isotope. Because what is the nice trick we can do is that the same element electronically behaves the same. So chemistry is all the same, but nuclear physics is different. So you see here, this is nuclear physics, because if I use a different isotope, I don't see anything. So we really managed to, for the first time ever in history, excite a nucleus using a laser or like light that is almost visible. And that has a beautiful exponential decay, as all processes that are just basic two-level systems. And luckily we had colleagues in the US that used a different crystal, LISEF, that confirmed our results. Also very important in science that you have competitors or collaborators that can confirm your results, because you never know if it's true if you're the only one. And and in general, very often you get scenes like this where you're just like sitting around in boxes, and I don't know, science is also messy, guys. So we did this laser spectroscopy, and then, so we knew now where the energy is. So the step 3 was compared to another clock, because then, only then, do you truly make a nuclear clock. So what we did, again, is now take our little crystal. It's there in blue, like you see the little tiny dot. Actually also here, there on the left, I forgot. There on the left, that's our tiny crystal in the whole setup. So here, again, that's there. And in the back is just something to align our laser. And so we, again, just shot a laser at our crystal and tried to measure it or compare it to a clock. So, and again, the lab situation with the people at Gilla. What did we do here? Well, we had a frequency comb, which I talked to you about. And the frequency comb was connected to the strontium clock there. So this is an established clock. It works. People know it's a clock. And we took that frequency comb, which is a laser, and through a process called higher harmonic generation, this HHG, I won't explain, we could increase the energy such that it was resonant with our nucleus and that we could do spectroscopy of the nucleus. And by doing this measurement, we could compare the thorium nuclear clock to the strontium clock. And then actually we came to a really funny result. Well, first of all, we did spectroscopy on the 200 kilohertz level. That's really tiny for the physicists out there. But you see there's more than one line, right? And we expected one. We didn't expect, like, at least back then, but I already gave the answer a bit. Like, if you put something in a material, it tends to interact, right? So step 4 was back to Hendrik, actually. So what we did was laser Mössbauer spectroscopy. So in the past, they always did it with radioactive material. We did it using lasers. So we did laser Mössbauer spectroscopy of a nucleus. And let me just explain you again for the last time, bear with me, like the physics. So if you have this thorium sitting in this crystal, and you have these 2 extra fluorides, right? You see them now. I actually have to tell you something. Nuclei are not spheres. They are, the heavy ones especially, are elliptical, like a rugby ball. And of course, you can see that there's more fluorides on one side than the other. This creates an electric field gradient. All right, there's more negative charge there and more positive charge there. And then actually what starts happening in this asymmetric crystal structure is that the nucleus can take many different positions in that field. And those are different. And you can tell the difference by spectroscopy. So this 2-level system that we started out with actually became a 5-level system. And all the lines in between were possible. And you can calculate exactly how this energy difference is. The important part is this. The VZZ is just a number, which is the electric field gradient. So how strong are these 2 charges? How strong is this asymmetry? And why is this important? Well, because we measured these 5 lines, and then we can do physics. We can fit, right? We can use our equations to understand. And then we can extract how strong this electric field gradient is. And then we can compare it to how strong it is for these different little configurations that we imagined at first, right? Because we imagined we were like being creative and we were thinking like, okay, which one of them is it? And it actually, at the start, didn't match with any of the things that we thought before. That's also what you usually notice in physics. You try to think very hard. I think the situation is like this, and then you do the experiment and it tells you, actually no. And so we did more measurements. And actually then we started to see more than 5 lines. We started to see, I think, about 20. And so, like looking even deeper in the material, because we had better lasers, better things, we started seeing even more interactions. And we actually then did another thing, which is we could actually, nowadays, it's really cool, nowadays you can take a device called an electron microscope and you can actually see atoms. We are at the point where you can just see atoms sitting, right? So here on the top right, also top right, you see lots of dots, right? Every one of those dots is an atom. And we can just see them. It's not even hard, actually. I could just like tell people, can you measure that for me? And then you see that some are brighter than the others. The brighter ones are the heavier elements. It's the thorium. So you can actually now even see the thorium that we put in our crystals, see in there. And then we figured out, actually, they like to sit next to each other. You see, like ever so often, there's a pair of 2. And that's why before it never matched with any of our values, because we didn't consider, actually, maybe they like to sit next to each other. And that's how nature, in this case, surprised us. And if you now look at this spectrum on the left, and you go back to the spectrum of Mr. Hendrik de Waard, basically, we're doing the same thing all over again 40 years later. Although nowadays we have more precise lasers, it's a different story, but in general, we're still like basically proving Einstein right. It takes very long, at least 40 years maybe, to get to something new, because we just started this field and now we get to the result where he maybe took his life for, and we can now take our life, let's say, to maybe get to a new point in the future. So with that, I would actually come sort of to an end and hope to sort of convey the message for you guys. Okay, what should you take home from all that I told you, right? So one thing is that modern clocks, they push the boundary of fundamental physics and applications. Because like GPS is already a bit old, but people are using clocks in many radical new ways. A very stupid example, for example, is measuring the height difference of where you start building a bridge and where you have to end building a bridge. This is actually harder than people might think. So you know, because you need to know where you need to end your bridge, right? And you need to calculate that very well. And you can use clocks to actually measure up to a millimeter in height difference. So if you just put 2 clocks and you compare them, you can tell them, okay, that one is 10 centimeters or 10.1 centimeters higher than the other one. And these things are still big and bulky and not commercialized, but this is where it's going. And we also see some weird signals that we're like, okay, this doesn't add up. So with just a little bit more precision of our clocks, we can probably find also new physics. But on the other hand, never forget about the history. After 40 years, we are sort of back where we started. And we're happy that people wrote down things so well that we can learn again from them and build upon them and continue, you know, standing on the shoulders of giants, as some people might say. But exactly all the new developments in laser spectroscopy, so also like where the Nobel Prize was won for the frequency comb, these things really push how precise we can be. And nowadays, I visited a lab today in Groningen. They're like, yeah, you can build these lasers yourself, and we used to do that, but now we just buy them from some company because like this is the state of the art of what you can get is so much easier that you don't have to spend your own time. And this is how society progresses, people. And then as a last point, science can be used for good and bad, and obviously our choices decide what happens. So with that, I would like to leave that, and I hope you think about your choices also for next Wednesday. And I want to thank, obviously, because this is not just me, right? I am now just the puppet conveying the message of actually tons and tons of people scattered across the globe. I think in total maybe like 100 people or more, which are all working enthusiastically on this, having a good time in life, but also spending many, many late nights many, many weekends to try and do these things for a not so favorable pay necessarily. Thank you very much for listening, and I wish you a good evening.
Before we end, we can take some questions.
Of course.
So, okay. Don't ask the question before I give you the microphone, so that people at home can.
I was wondering if the scarcity of this specific isotope hinders the mass production of these kinds of clocks.
A very good question. Very good. So yeah, I mean, I already said, like, we have 12 milligrams of the material. So one of our problems, why did we have to make these crystals so small, is because we just don't have much of it, right? So, and everything comes from Oak Ridge in the US. And yes, we are thinking about, because people are even thinking about commercialization already of this technology. It would be maybe only working in 10 to 15 years or never, but people tend to think ahead. And then the question is, we already asked ourselves, can you produce more of this? The answer is yes. You would need nuclear reactors, though, for it. How much, though? That's hard, right? Because exactly, like, to produce large quantities of something is rather difficult. But I think that if governments would want this, it will happen. It's not an unreasonable amount. And mainly what we see, what I didn't tell, actually, is that what we're measuring now as well, is that in our crystals, when we increase the concentration, we actually get a worse clock. So we actually are tending towards putting less and less in there. That's also, I guess, what technology does, right? Everything's smaller, more efficient. So in general, we're going to go to points where we have to put less in there. Our growth processes are more efficient. And yeah, some production needs to happen at some point. But the nice thing is it's automatically produced, right? Because this uranium-233 is just lying in a bunker in US, and it automatically, just by radioactive decay, you can't stop it, produces the thorium. And that is, they call it milking. They milk it off, like every year. Out of the big block of uranium, the big block of death, they just milk it out, let's say. That's what happens. Okay.
Yeah, thank you for the interesting talk here. Can you give an indication about the accuracy of this new clock material? How good can you measure a second or a part of a second?
Yes. So I didn't went too much into this detail, but so like I said, so the GPS needs to be precise on the 10 nanosecond level, right? Nowadays, optical clocks, which are, I have to say, very far developed already, right? So the ones that they are based on atoms are quite well developed, and they reach precisions of 10 to the minus 19. This means that 19 zeros, so that is the amount of seconds they run off every second. That means it takes 10 to the 19 seconds, which is probably, I don't know, 1,000 times the lifetime of the universe, before it, like, the clock goes off by 1 second, right? And then the question is, what would be the precision, right? Not accuracy, precision of this clock. We expect that, so it can be slightly better, but not super much so. So we expect maybe 10 times better. But the strength, it really lies in that it's such a different system. So we actually want to have both clocks, one electronic clock and one nuclear clock that one can compare. And the thing is just that, well, by the time we get to where they were 20 years ago, they will be 20 years in the future, right? So in that sense, people are trying to develop many technologies simultaneously. People are looking at highly charged ions, if that makes any sense. It does something about plasma, highly charged ions. I was talking there, never mind. So people are finding new ways to make also clocks based on atoms, and you don't really know which one will be better in the end, but this one will be maybe 10 times better than the best that we have now. And the main benefit is still it's less sensitive to external perturbations. So that's why this commercial aspect is something that people are really looking at, because this is a system you don't need a vacuum system for. You put it in a small crystal, you can bang it, you can bring it around, and nothing will happen to it, because these nuclei are frozen. So I think that and being a probe for different forces are the main winning points, I'd say.
Thank you very much for the lecture. My question is, please, about dependence of time according to whether there is matter or no matter. Like velocity is also connected to matter, and acceleration as well, but time as well, I guess. And
you say dying mass?
Yeah, time.
Sorry.
The thing which is your lecture about. But yeah, what about time if there is no matter available, like
would there be time?
Between stars or galaxies, for example, but also between a large space relatively between the nucleus of an atom and the electrons far away. That's also a kind of vacuum. But what is the meaning then of time in even such tiny spaces?
That's a good question. Like what? Because I actually once was on a hike in Colorado, and then a man found me, and he was like, "Oh, I'm into this Buddhist thing now, where I don't know, they are thinking about does time really exist?" And then we discussed for a moment, and then the thing is exactly this point of like, okay, as humans, for us, time exists. There's no reason to believe that time doesn't exist, or like time is, for us, a very useful and relevant concept. And I think you can prove that in the end, you cannot really prove that anything exists, but you have to think about if something is relevant and useful to you. So thinking about our lives in terms of time is very useful. Now, for the nucleus, how does progression of time go, right? In this small space, what does time still mean? Well, exactly, the smaller you go, the less more ill-defined time would be. And of course, I'm not an expert in this, I know, and I talk to some people who are interested in this. And yes, then you start asking yourself the question, like, what happens between two fundamental interactions? So if a particle, because you have quantum physics, as some people might know, which means that if I don't measure a particle, I don't know where it is, right? And so I kind of, in a way, also don't know what time progresses there. And so in that sense, apparently what we see, I guess, to the precision that we have, in nuclei still time works as time works, but we might hit a limit at some point, and that's also obviously something that we are interested in to see. And yeah, the more fundamental you go, at some point you would hit a point where you could see, this is the fundamental single progression of time. At least that's what we think at the moment, but nature tends to surprise us, so we will see. I would say. I don't know, and time is a very vague concept, which works for us, but maybe not for neutrons and protons. More questions. Can also be about politics, can be about philosophy. I enjoy talking in general.
Thank you very much for your lecture. I was wondering the behavior of the crystals under pressure or under skew forces.
Yeah. So we didn't study any of this yet, so we don't know. Obviously, something would probably happen, but probably it will mostly show up as changes in this electric field gradient I talked about. And maybe you would get phase changes in the material, meaning it under so much pressure, it would like to order itself differently. I don't think there's a good reason to believe it would really affect the nuclei, but this is with a, I'm not gonna, because I do know that apparently if you hit, I heard this from some people, apparently if you hit a piece of uranium that's fissile, let's say, with a hammer, something happens. This kind of means that exactly pressure can also have effect on nuclei to a certain degree. Sorry, what do you mean with the structure?
Can affect the structure of the crystal.
Yes, so you would see like this shock wave and this phonon. Recently also papers came out where they see the coupling between phonons and nuclei. So there is definitely something there. There's probably lots of interesting things to do there. I think what we're figuring out at the moment mostly is that the nucleus is moving around a lot in the crystal, more than we expected, and it's a very new perspective we're taking. So the nucleus is doing this effectively, but still you see these narrow lines. So there's some sort of fundamental insight that exactly has to do with crystal structure and torsion. I would say we don't really know, but there's definitely something there. Yeah. Oh, there's something in the back as well.
Again, also thank you for your lecture. I was wondering maybe, as a more general question, what is now the outlook for the research? Because you've now proven that this works as a clock. Mm-hmm. What is it that you're currently thinking, oh, this is the next step in this development? So
at the moment, it's kind of a bad clock. It's really much worse than anything else that exists. That's not true. Like it's better than a pendulum clock, but worse than a quartz crystal, which most people have in their watches. So the next steps are really trying to make this work. And then you have to ask yourself the question, can we get further in the crystal? Because actually we've already hit the first limit of the crystal. I didn't show that, but we actually measured, our laser is more narrow than the line we measure in the crystal. And that is bad because the more narrow the line in the crystal is, the more stable the frequency, right? This has to do with this Q factor, that the stability of the frequency is important. And we obviously want that the nucleus is better than our laser because then we're limited by our technology, not by nature. And there's something in the crystal, again, that's sort of messing with our nuclei. This is logical on one hand, but we don't really understand fully why. So that is one direction we're getting into, and especially what I was saying. So that's one direction. But also people are building ion traps. So they are actually doing the same trick as the other optical clocks, just put it in vacuum. It's the simplest solution. So people are doing it in vacuum, but they didn't manage to do spectroscopy there yet because of the scale advantage. We have 1 billion atom nuclei, and they have 1 or 2. So in that sense, those two different pathways are being pursued at the same time. And the ion trap will definitely make a really good clock really quickly. The crystal approach will probably struggle with lots of sort of new physics, or kind of like old physics in a new jacket, that we will hurdle over. And some people believe in this direction, some people believe in this direction, but I think in the end it's just important that we study both. So effectively what we're doing is we're trying to grow better crystals at the moment. We are developing better lasers. We are thinking about what if we cool our crystal, what if we make it really small, what if we're also trying to find new ways to detect. We are actually using nuclear magnetic resonance, NMR, to try and detect things in our crystals. So we're actually just widening up again. We're trying to use lots of new different techniques to figure out, can we do something better in the crystal, while just doing the brute force method of trying to make the ion trap work.
I think we have time for one more, and then the other questions can be asked during the drinks. So here you go.
Oh, it's fine, okay.
Sure. Hi. I just wanted to ask, would it be possible to align all the nuclei in the crystal? Because it sounds a little bit similar to magnetic resonance imaging to me, from a medicine standpoint, where you can then align all the water atoms and then see how they go. So would it be possible to align the nuclei and then solve that problem?
So this aligning has to do with the fact that this is your problem of broadening your line, right? So the thing is that, with MRI, that's NMR, by the way, it's the same thing. The thing is that there you align because everything is, the dipole is randomly oriented. But heavy nuclei like this don't have a dipole. They have mostly a quadrupole moment, which is not really orientable, let's say. So this is a problem that's not really so, the orientation is actually not so important to us, we think, at the moment. We actually, probably what we can do actually is not orient the nuclei, but probably there's defects and contaminations around that do have a dipole, and if we orient those, we have less negative effect of those on our nuclei. So there is some correct points to say, but like I said, we are now, this just came out, right? This is measurements done like 2-3 months ago or so. So we're still trying to figure out, okay, what is actually happening? But yeah, actually, one of the obvious things to do would be put a big magnet around it and see what happens. That is probably faster than trying to think your way through. But it's not always so easy because now we need a big magnet and we probably need to cool down our crystals, so you need a cryostat. And honestly, I think one of the biggest problems in physics is that you don't have a guy close by because everyone is specialized in their own little technique. We're all spread out and we're all busy with other things because this is obviously interesting, this nuclear clock. But there's also really a lot of other things that are very interesting, right? So you need to find somebody who's interested and has time, and then you can continue this. So I think our problem would be, yeah, if there's somebody who's like, yeah, I'll take a radioactive crystal and put it in my NMR machine, and you can shoot it with a laser, etc. I take it.
Thank you.
Well, with this, let's give Kjeld a round of applause. Again, thank you all for coming. It was a great lecture. Thank you, Studium Generale, for having us and helping us with the organization. And thank you to the De Waard family for all of the support through the years, and we're really grateful you're here. We have a gift for you, which of course you don't have to open right now, but this is a sign of our appreciation. And thank you for being here. And if you're interested in what Studium Generale has to offer, their next lecture in English will be about the bridge between politics and science, actually. So check out their website, and if you're interested, please come. So with that, thank you again, Kjeld, and we're going to have drinks downstairs in Spiegerzaal. The Dutch people, you can correct me if that was wrong. So if you have more questions, you can ask them there. Yeah, thank you for coming, and thank you, Kjeld.
Thank you.